Okay. Hello, everyone. My name is Roberto Rubboli, and I'm talking about fundamental limits on correlated catalytic state transformation, and this is a joint work with Marco Tomamichel at the QIP. So first, I will introduce catalytic resource theory. So I will just briefly mention resource theory and then catalytic resource theory. Then I will state our main result and how our main results applies to three specific resource theory, namely abnormality, and pure state entanglement theory, and resource theory of coherence. And then I will state some conclusion and talk about some open questions. So the introduction, a quantum resource theory is defined by a set of free states, which is a subset of all quantum states, and a set of free operation, and free operation map free states into free states. I introduced this general framework to state our results in the most general way. So in its resource theory, I will specify, for our work, I will specify the set of free states, and our results apply to any resource theories that is compatible with the set of free states. So first, the resource theory of abnormality. Here we have just only one free state, which is the thermal states. And just to discuss the first statement, for example, our results apply to resource theory of abnormality under Gibbs preserving maps or thermal operation, because they both keep the Gibbs state invariant. This is just an example. Or then we have entanglement theory. Here the free states are separable states. And I mentioned here we will consider pure tape entanglement theory in the bipartite setting. And then resource theory of coherence. And here free states are diagonal states in a particular basis. I will introduce free operations. So I have an input state rho. I want to transform rho with a free operation n into a state rho prime. What we can do is we can use a catalyst, and here is our work. So actually we want to characterize these catalytic operations and find some fundamental limits and discuss those operations in the most general framework, which is given by the resource theories. So we can add a catalyst, and so we have an input state rho tensor ni, and we get a state, an output state rho prime tensor ni. And here note that there are no correlation in the output state, and we will call them CO, so catalytic operations. What we can do, we can allow for some correlation in the output state. So in the output state, rho prime might be correlated with ni, and we will call those operations correlated catalytic operations. And another thing is embezzlement. Here, the catalyst might change after the transformation, and this is called embezzlement. So I want to give an example of this characterization. This is classical resource theory of abnormality. So the set free O is described by this ordering relative thermomajorization in this case. So we have a probability PQ majorize a probability P prime P prime Q prime if there is a stochastic map transforming P into P prime and Q into Q prime. Here you just put Q equal to gamma. And for CO, we need the ordering of the Riemann divergences, which is this kind of constant by log and the sum of the components of this vector. You can see the formula 1. And we require all the ordering for all the Riemann divergences bigger than 1/2. And for CCO, instead, we required only the ordering of one of those Riemann divergences, which is the one for alpha equal to 1. And here it comes the main idea, basically, of our theorem, which concerns correlated catalytic operations. I will talk about it later. So here we have an example. Here is the set, is the simplex, so the set of all three-dimensional classical states. And here we have an input state P, and the region, the most blue one region is FO, so the set we can achieve with free operation. We can reach more states by allowing a catalyst, but not correlated, and here CO. And then we have CCO, which is still a bigger, larger set. And the red region is are the points that will concern our main theorem, and they are kind of the hard states to achieve, for which the catalyst, as I will mention, needs to be highly resourceful. So our main results, first I will state a formal definition. rho can be transformed in rho prime by an epsilon catalytic transformation if there is a free operation and a catalyst state nu, such that rho tensor nu is mapped into tau, and the catalyst preserved, so the trace over tau is nu, and tau is epsilon close to rho prime tensor nu. So basically there are correlations between rho prime and nu. It's not really a product state. And if this holds for any epsilon bigger than 0, we say that rho is transformable into rho prime by correlated catalytic transformation. We quantify the closeness of rho prime tensor nu and tau with the purified distance, which is just the square root of 1 minus the fidelity. So here is our main theorem. This is geometric picture. So first I introduce this quantity, which is the fidelity between a state and the set of free states. So I just maximize over the set of free states. And our main results states that for an epsilon correlated catalytic transformation, the fidelity must be smaller than a constant multiplied by epsilon. So this means that as epsilon goes to 0, the catalyst state nu must be farther from the set of free states. Yes, and this means actually by an entropic relationship that the resource of the catalyst must go to infinity as epsilon goes to 0. So this is actually the quantity we want to look at. So we introduce the resource monotone d of rho, which is just the minimized version over all the free states of the Umegaki relative entropy. And in the resource theory, we consider this quantity completely characterized the set CCO. So what I mean is that if there is this ordering of this quantity, we can actually have the transformation. I will talk it about better later. And for the resource theory, we will consider, we identify this quantity as the right quantity to quantify the resource of the catalyst. Here, maybe for us, it was not actually enough to bound the dimension of the catalyst, the dimension of the Hilbert space of the catalyst, but we want to look at a quantity that actually quantify the resource of the catalyst, for which we can say it's hard and it contains high resources. And that's our main theorem. So consider resource theory for which f is multiplicative. Then if you have this ordering of the fidelities, f of rho is bigger than f of rho prime. To transform rho into rho prime, we need the fidelity of the catalyst smaller than epsilon, a constant multiplied by epsilon. So the catalyst must be far from the set of free states, and this means that we have a logarithmic divergent 1 over epsilon of the resource monotone D that characterizes the resource of the catalyst. So as epsilon goes to 0, so as the correlation between the catalyst and the output stage goes to 0, the catalyst must be infinitely resourceful in the case epsilon equal to 0. That's the limit, basically. So we show that our bound is optimal. Indeed, we can actually achieve by a procedure, if it's a well-known procedure known as asymptotic to catalytic reduction, we can actually perform this operation, and we have the upper bound O log 1 over epsilon that matches our lower bound. And actually, our theorem also if we don't perfectly recover the catalyst. So I'm not talking much about that, but we recover the bounds given first for the embezzlement, lower and upper bound, and we extend the lower bound for embezzlement to any resource theory. So let's talk about the 3 specific resource theories. So first, fidelity here is trivially multiplicative, and you can check our paper. We can build actually these states, this kind of hard state that can be transformed with correlated catalytic operations, and there is this other ordering of the monotone F. And here in this case, we have the free energy, and the free energy diverges with the correlations. So the free energy of the catalyst, we would need to prepare a catalyst with infinite free energy as the correlation goes to 0. Then pure state entanglement theory, here we consider output bipartite pure states, essentially because we have the multiplicative results for the fidelity only for pure states, and which is a condition of our theorem. And then we can show that there are these states, and so we can actually state our theorem, and so our theorem doesn't apply to an empty set, basically. And in this case, the entanglement entropy has this logarithmic divergence with the correlation. So we will need to prepare to transform. We will need to prepare a catalyst with an entanglement, a diverging amount of entanglement. And for resource theorem of coherence, the fidelity is multiplicative. We actually find an Alberti form for this fidelity, and it was already known that the fidelity was multiplicative, but we kind of recovered independently, and we give this STB form to efficiently compute the fidelity for mixed states. And we still build this kind of states, and we show from the Million theorem, it follows that in this case, the amount of coherence diverges with the correlations. So I want to give you maybe first a sketch of the proof. So the main ingredient, one of the main ingredients is to prove data processing for smoothed ascending quantum Rayleigh divergences for alpha equal from 1/2 to 1, and this is actually non-trivial. And if you notice what, so we have this sandwich of minimal Rayleigh divergences, and we smooth. So we actually maximize the quantity by smoothing the input state over an epsilon ball around rho. So all the state rho tilde around rho. And yes, and we actually found out that to prove data processing, we actually need to allow some sub-normalized states, and otherwise it will not satisfy data processing. And to prove the results, we take advantage of the Stein spring dilation. So first we prove it for isometries and then partial trace. So for isometry, first we prove that the optimizer and the output state we can restrict it to the support of the image of the isometry, and then we construct the relative pre-image on the input state. And basically we use data processing of just the sandwich Rayleigh divergence. And then for partial trace, we use that if you have these states that are epsilon close in the input space, in the composite space, we can still find states with those marginals that are still epsilon close. And we actually argue why it is not possible to do this for Petz Rayleigh divergences, and we show it basically relying on invariance of the quantity under embedding in a larger space. And in this case, we prove that it's not actually possible to prove in this way a data processing for Petz Rayleigh divergences. And here is the main part of the theorem. So we introduce this monotone, the mean, which is of rho, which is just minus log f fidelity of rho. I just introduced before the fidelity of rho, which is the distance between a state rho and the set of free states. And we choose for our theorem two states, rho and rho prime, such that the mean of rho is smaller than the mean of rho prime. And this for some additivity arguments, that it means that rho prime doesn't lie in CO, so it cannot be transformed with correlated operation, so without correlations, but it can be transformed with correlations because this quantity d mean is not super additive. So we have both these conditions exactly. So the first one, it's related to catalytic operation. The second one is correlated catalytic operations. And we have a, rho prime is epsilon close to tau. We have a kind of conflict between these two, and it can be only resolved only if the fidelity of the catalyst is small. And here is the main inequality. So first we have the epsilon mean of rho tensor. We have this difference. So the second, in the first line, the second term is just the same one, and the first one we just use data processing for smoothed quantities. This is just a resource monotone, but it's a corollary to prove that from it also from the monotone. And then on the left hand side, we use a tight inequality for the purified distance, and we relate it to the fidelity. So basically, the two quantities on the left are minus log fidelity. So then we use the relationship with the purified distance, use the triangle inequality to the purified distance, and we find the second term in equation 10. And a gamma is an epsilon factor because the optimizer is epsilon close to rho tensor ni, and f is just this quantity which is multiplicative by assumption. And then we can just solve the inequality for f of ni, yes, and then in the final result, it's matter of calculation. We can bound the square root of f of ni with epsilon multiplied by a constant. This is basically the data processing gap, the constant between f of rho and f of rho prime. So the conclusion is we focus on the catalyst preparation, and our results apply to any catalytic resource theory. And we show that there is a trade-off between the residual correlation, the resource needed to prepare the catalyst, and we establish that our lower bound is optimal. And we extend the already existing lower bound embedding transformation on any resource theories. And some more open question. So the states of our theorem are those hard states which for which f of rho is bigger than f of rho prime, strictly bigger, that lie in the right region, which is out of CO but in CCO. So the question is, does the same holds for all the states that are out of CO but inside CCO? And the second question is, when we compose this catalytic operation, what actually happens? Because, for example, if we have two catalysts and we want to transform rho into rho prime using the first catalyst and then rho prime into double prime using the second catalyst, then the two catalysts might get correlated. This is still an open question. It might be worth thinking about it. And the question is, are actually correlated catalytic transformation closed under composition? Because here we start with a catalyst, basically, in this composition of operation, basically we start with new tensor new 1, tensor new 2, and then we end up with new 1 correlated with new 2, and so the catalyst is kind of spoiled because, okay, anyway, I finished. Okay. Thanks for the attention. It was the last slide.
Oh. Yeah, so we have time for questions. If you have any, please come forward.
I don't know actually what happened, but it was the last.
So thank you very much. That was very nice results. So do you have a feeling for whether or not being very resourceful is also sufficient? I mean, if you give me a catalyst which is very resourceful, is this going to be a state which is very resourceful? Is this likely to be a good catalyst, or do you need more than this? Do you have a, I mean, vague, but
actually, we don't know. Actually, the procedure in which we rely on performing this catalytic operation is this asymptotic catalytic reduction that holds for both for correlated operations and catalytic correlated operations. So when you actually have input to output state, you can kind of take many copies of rho and rho prime, if you call them, and build this catalyst state that has these properties and follows this bound, which is actually, it saturates the bound. And so we know that that catalyst can perform the operation, but actually we don't know much more. We just have this optimal procedure, and and that's what people do. Also in the talk before, that's how you perform this kind of operations.
yeah, I completely understand. It's just more to get a feeling. Like Patrick and I were very interested in what makes a good catalyst, and you seem to be getting make good progress on this question. I just wonder if this is enough, or is there more to? I mean, how much more do we need? Where do we need to go from here? Maybe we can talk about it.
Okay.